Imagine a place in the universe where the rules of reality as we know them cease to apply. A cosmic enigma so powerful that it warps space, distorts time, and devours everything, even light itself. This is the realm of the black hole, one of the most profound and mysterious phenomena in the cosmos. To understand a black hole is to grapple with the very fabric of the universe, to peer into the extremes of physics, and to confront the limits of our comprehension. In this exploration, we will journey into the heart of these celestial titans, unraveling their origins, properties, and the profound questions they pose about the nature of existence. Black holes are not mere objects. They are regions of spacetime where gravity is so intense that nothing, not even light, can escape their grasp. The concept of a black hole stretches our understanding of physics to its breaking point, blending the elegant simplicity of Einstein's theory of general relativity with the strange and counterintuitive world of quantum mechanics. They are born from the deaths of massive stars, sculpted by the relentless force of gravity, and they challenge our perceptions of space, time, and matter. Let us embark on a journey to understand what a black hole truly is, how it forms, what it does, and why it captivates scientists and philosophers alike. To comprehend a black hole, we must first look to the stars, not the twinkling points of light we see in the night sky, but the colossal furnaces of plasma that power the universe. Stars are born from vast clouds of gas and dust, collapsing under their own gravity to ignite nuclear fusion in their cores. For millions or even billions of years, they burn brightly, fusing hydrogen into helium and heavier elements, radiating energy that sustains planets and, in some cases, life itself. But for the most massive stars, those with masses at least 8 times that of our Sun, this journey ends in a cataclysmic finale that gives rise to a black hole. When a massive star exhausts its nuclear fuel, the delicate balance between its outward-pushing fusion energy and the inward pull of gravity collapses. Without the pressure of fusion to hold it up, the star's core succumbs to gravity's relentless force. In a fraction of a second, the core collapses, compressing to unimaginable densities. The outer layers of the star, no longer supported, come crashing inward, triggering a supernova explosion, a cosmic detonation so bright it can outshine an entire galaxy for weeks. What remains after this violent outburst depends on the star's mass. For stars with cores above approximately 3 solar masses, the collapse does not stop. The core continues to implode, shrinking beyond the limits of known physics until it forms a singularity, a point of infinite density where the laws of space-time break down. Surrounding this singularity is a region called the event horizon, a boundary beyond which nothing can escape. This is the black hole, a gravitational abyss that marks the end of one story and the beginning of another. Not all black holes form from stellar collapse. Some, known as primordial black holes, may have formed in the chaotic aftermath of the Big Bang, when pockets of dense matter collapsed under their own gravity. Others, dubbed supermassive black holes, lurk at the centers of galaxies with masses millions or even billions of times that of the Sun. Their origins remain a mystery, though they may have grown from smaller black holes merging over cosmic time, or from the collapse of massive gas clouds in the early universe. Regardless of their origins, all black holes share one defining trait: their insatiable gravitational pull. A black hole is not a tangible object in the way we think of stars or planets. It is a region of spacetime defined by its gravitational influence. At its heart lies the singularity, a point where density becomes infinite and the laws of physics as we know them cease to function. The singularity is a theoretical construct, a place where our equations fail and we are left with more questions than answers. Is it truly a point of infinite density, or does quantum mechanics intervene to prevent such an extreme? We do not yet know. Surrounding the singularity is the event horizon, the point of no return. This invisible boundary marks the edge of the black hole.
Anything that crosses the event horizon, be it matter, light, or information, is lost to the outside universe. The size of the event horizon, known as the Schwarzschild radius, depends on the black hole's mass. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers, 1.86 miles. For a supermassive black hole with a mass of 1 billion suns, it could stretch across billions of kilometers, larger than our solar system. Beyond the event horizon lies a region of intense gravitational effects. For a rotating black hole, known as a Kerr black hole, this region includes the ergosphere, an area where space-time itself is dragged along by the black hole's spin. Objects in the ergosphere can still escape, but they are forced to move in the direction of the black hole's rotation, a phenomenon known as frame dragging. This is one of the many ways black holes warp the fabric of space-time, creating effects that defy our everyday experience. The concept of a black hole was first theorized in the 18th century by Jean Michel and Pierre-Simon Laplace, who speculated about dark stars with gravity so strong that light could not escape. But it was not until 1915, with Albert Einstein's publication of general relativity, that the modern understanding of black holes began to take shape. General relativity describes gravity not as a force, but as a curvature of space-time caused by mass and energy. Black holes are the ultimate expression of this curvature, bending space-time to such an extreme that it creates a cosmic trap.
To understand a black hole's behavior, we must delve into the strange and wondrous world of general relativity. According to Einstein, massive objects warp the fabric of space-time, much like a bowling ball on a trampoline. Near a black hole, this warping becomes extreme. As an object approaches the event horizon, the gravitational pull grows stronger, stretching space-time and altering the passage of time itself. One of the most striking effects is gravitational time dilation. To an outside observer, a clock near a black hole would appear to tick more slowly than one farther away. As an object approaches the event horizon, time slows to a crawl, and at the event horizon itself, it appears to stop entirely. This is not an illusion, but a fundamental consequence of gravity's effect on space-time. For an astronaut falling into a black hole, however, time would seem to pass normally. They would cross the event horizon without noticing anything unusual, though they would soon face a grim fate. This brings us to another bizarre phenomenon: spaghettification. As an object approaches a black hole, the gravitational pull on its near side is far stronger than on its far side, creating a tidal force that stretches the object into a long, thin shape, like spaghetti. For a stellar mass black hole, this effect would tear apart any object well before it reached the event horizon. For a supermassive black hole, with a larger and less dense event horizon, an object might survive closer to the boundary before being destroyed. Light itself is not immune to a black hole's grasp. Because light follows the curvature of space-time, a black hole bends light rays around it, creating a phenomenon known as gravitational lensing. This effect can distort the appearance of distant stars or galaxies, magnifying or warping their light as it passes near a black hole. Gravitational lensing has become a powerful tool for astronomers, allowing them to study distant objects and confirm the presence of black holes. If black holes emit no light, how do we know they exist? The answer lies in their influence on the surrounding universe. Black holes reveal themselves through their gravitational effects, their interactions with matter, and the strange behaviors they induce in nearby objects. One of the most direct ways to detect a black hole is through its effect on a companion star in a binary system. If a black hole orbits a visible star, it can pull material from the star, forming an accretion disk, a swirling, glowing ring of gas and dust spiraling toward the event horizon.
As this material accelerates and compresses, it heats up to millions of degrees, emitting X-rays that can be detected by telescopes like NASA's Chandra X-ray Observatory. The first confirmed black hole, Cygnus X1, was discovered this way in the 1970s, based on the X-ray emissions from its accretion disk. Another method is to observe the motion of stars or gas clouds orbiting a black hole. At the center of our Milky Way galaxy lies a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. Astronomers have tracked the orbits of stars near Sagittarius A star, observing their rapid elliptical paths, evidence of an immense invisible mass. In 2020, the Nobel Prize in Physics was awarded to Reinhard Genzel and Andrea Ghez for their decades-long observations of these orbits, which provided definitive proof of a supermassive black hole at our galaxy's core. Perhaps the most stunning evidence came in 2019 when the Event Horizon Telescope, EHT, captured the first direct image of a black hole. Located in the galaxy Messier 87, M87, this supermassive black hole, with a mass 6.5 billion times that of the Sun, appeared as a dark silhouette surrounded by a glowing ring of gas, the accretion disk, warped by gravitational lensing. The image, a triumph of global collaboration and cutting-edge technology, showed the shadow of the black hole's event horizon, confirming predictions of general relativity with unprecedented clarity. Black holes also make their presence known through gravitational waves, ripples in spacetime caused by massive objects accelerating, such as two black holes merging. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first gravitational waves from the merger of two stellar mass black holes, a discovery that earned the 2017 Nobel Prize in Physics. Since then, LIGO and its partner observatories have detected dozens of black hole mergers, opening a new window into the universe's most violent events. While generally relativity describes the macroscopic behavior of black holes, the microscopic world of quantum mechanics introduces profound challenges. One of the most famous is the information paradox, first articulated by physicist Stephen Hawking. According to quantum mechanics, information about a system, such as the properties of particles falling into a black hole, should never be lost. Yet, if a black hole swallows matter and later evaporates, what happens to that information? In the 1970s, Hawking proposed that black holes are not entirely black. Through a quantum process now called Hawking radiation, black holes can emit particles near the event horizon, gradually losing mass and energy until they evaporate completely. This discovery was groundbreaking, as it suggested that black holes have a finite lifespan. However, it also raised a paradox. If a black hole evaporates, does the information about the matter it consumed vanish with it? This violates quantum mechanics, which insists that information must be preserved. The information paradox remains unresolved, though recent advances suggest that information may be encoded in the Hawking radiation itself or preserved in a way we do not yet understand. Resolving this paradox requires a theory of quantum gravity, a unification of general relativity and quantum mechanics, that remains one of the holy grails of modern physics. Another mystery is the nature of the singularity. General relativity predicts an infinitely dense point at the heart of a black hole, but quantum mechanics suggests that infinities are unphysical. Some theories propose that quantum effects prevent the formation of a true singularity, replacing it with a region of extreme but finite density. Others, like string theory, suggest that black holes may be complex structures of fundamental strings or branes. These ideas remain speculative, as we lack the experimental tools to probe the interior of a black hole. Black holes are not just cosmic curiosities. They play a profound role in shaping the universe. Supermassive black holes, found at the centers of most galaxies, influence the formation and evolution of galaxies. Their immense gravity can trigger star formation by compressing gas clouds, while their energy output, through jets of radiation and particles from the accretion disk, can regulate star formation by heating or expelling gas. These jets, often spanning hundreds of thousands of light years, are among the most powerful phenomena in the universe. They can outshine entire galaxies and shape the large-scale structure of the cosmos. The interplay between supermassive black holes and their host galaxies is a complex dance, with black holes both fostering and limiting the growth of the galaxies that they inhabit. Black holes also serve as natural laboratories for testing the laws of physics. Their extreme gravity allows scientists to probe general relativity in regimes where its predictions are pushed to the limit. The detection of gravitational waves from black hole mergers has confirmed Einstein's theory with remarkable precision, while also hinting at possible deviations that could point to new physics. The study of Hawking radiation and the information paradox could unlock the secrets of quantum gravity, revolutionizing our understanding of the universe. Beyond their scientific significance, black holes capture the human imagination. They evoke a sense of awe and mystery, representing the unknown and the unknowable. In popular culture, black holes are often portrayed as gateways to other dimensions or time machines, as in films like Interstellar. While these depictions take artistic liberties, they reflect the profound questions black holes raise about the nature of reality. Philosophically, black holes challenge our notions of existence and permanence. The idea that matter, light, and even information can vanish into a black hole forces us to confront the impermanence of the physical world. The singularity, with its infinite density, raises questions about the limits of knowledge and the boundaries of science. Can we ever truly understand what lies beyond the event horizon, or are some mysteries destined to remain unsolved? Black holes also remind us of our place in the cosmos. They are relics of the universe's violent past, testaments to the immense forces that shape galaxies, stars, and planets. Yet they are also strangely familiar, born from the same processes that created the elements in our bodies. As Carl said,
What is a black hole? It is a region of space-time where gravity reigns supreme, a cosmic crucible where the laws of physics are tested and transformed. It is the remnant of a star's death, the heart of a galaxy, and a puzzle that unites the macroscopic and microscopic realms of the universe. Black holes are both destroyers and creators, devouring matter while shaping the cosmos. They are paradoxes wrapped in mysteries, challenging our understanding of reality and inviting us to explore the unknown. As we stand on the threshold of new discoveries, black holes remain a testament to the universe's complexity and beauty. They remind us that the universe is not just a collection of stars and planets, but a tapestry of forces, ideas, and possibilities that we are only beginning to unravel. In the words of physicist John Wheeler, who coined the term black hole, they are the simplest, most perfect macroscopic objects in the universe. Yet they are also the most profound, holding secrets that may one day redefine our understanding of everything.